All right. Woohoo. Okay. So after that couple of talks, we're going to get a little bit more technical. I've got with me right now Ilay Grigorik, who's from Google. He's very active in the world of web performance. He's chairing the W3C's web performance group, and he basically wrote the book on web performance. So I have the book here, so anyone who's got this will know all about web performance. Ilay, I wanted to ask you, I actually wanted to tell you a story. Last week I was in London, and a friend I've known for years who I'd never seen flew over from Australia. And I said to him, how's it going being in London? And I expected him to say something about the weather. And he said, the internet is so much better here. And why is that? Why is Australian internet so poor compared to the UK? It's nothing to do with policy, is it?
Well, I guess it depends on exactly what he meant, but my guess would be, and you can tell me if I'm right or wrong, a lot of it has to do with latency, and the punchline there is physics, damn it. So we can talk about, I guess, more about why that's the problem, and I'm actually curious, what was his experience?
So his experience was that websites were snappy. Right. So they came up like this.
Yep.
And so the problem is that Australia is far away, right?
Yeah. So fundamentally, physics, damn it, speed of light, pretty fast, but not fast enough. And unfortunately, we haven't figured out how to make it any faster. So if you actually look at the distances and you say, well, I'm sitting in London or say New York, and I need to travel to Sydney, even if you pick the fastest path between those 2 points, one way it's roughly on the order of like 60 to 70 milliseconds. Now, you're not going to find any cable that's going to be a straight path between those cities, so you're going to bounce around, add some latency there. Also, we can't actually approach speed of light. We're pretty close, within like a constant factor, 1.2, 1.3-ish. You multiply all that out, and that round trip to just say like hello is 150 milliseconds. And it turns out that like humans can perceive change on the order of 200 milliseconds. Right? So you have to be incredibly responsive. And if you happen to live in UK and you're contacting a UK server, that's a huge difference. And I'm guessing that's exactly what he observed.
Right. I think he was probably contacting websites that were hosted far away from Australia. Yeah. And what's strange, though, is that, OK, so it's 150 milliseconds or whatever, and we can perceive that. How does that add up into a problem when I'm browsing a website?
Well, it's not just one round trip, right? So you send I want to see this page. The server has to do some bunch of stuff, calculate, compute what it wants to present to yourself, and then it sends back basically a manifest of things saying like, here's the text that you were looking for, and by the way, there's also this beautiful video that you want to see. You need to fetch this other information for the JavaScript that needs to run, the CSS, all of that needs to compose, and by the time you fetch that JavaScript file says, I need to also fetch this other thing, and then like 10 layers deep, you're finally resolving that dependency graph, and 2 seconds or 3 seconds has passed, and you finally see something on the screen. And that's kind of the fundamental challenge of building efficient applications on the web today. It's just understanding that graph, making it as shallow as you can, and maybe narrower in terms of the amount of data that you have to fetch.
And now, over time, right, we've gone from sort of 28.8 kilobit modems to 56, and now maybe if you're in San Francisco, you've got a very, very fast, big, fat connection to the internet. At the same time, websites, at some point they got usable. They were unusable at some point. And then they seem to have stopped getting faster. What's happened there? Why aren't they getting faster?
Good question. So networks are definitely getting faster, right? Like that's a given. I think our expectations have obviously changed as well. The websites, back when we loaded them, 56K modem, were much lighter, but we didn't expect rich video and 4K video and 60 frames per second and super high resolution images and all that stuff. So I think you can confirm this as well. Anytime you deploy a new link that adds extra capacity into the network, somebody else on the network notices that and says, oh, really? I can double my bit rate in my beautiful videos? Turns out users like that, and immediately that link is saturated, right? So what you thought is going to be your extra capacity for the next year is like saturated the next day, and it just means that you had pent-up demand that was not being used.
Yeah, this is a bit like making a highway even larger and more cars say, OK, I can use that, and you're back to where we were. Exactly. We see that quite commonly where we add extra bandwidth, thinking, oh, that's good, we need the extra capacity, and it instantly fills up.
Yep.
And what's actually happening is someone goes to a website, the website now operates more quickly because we have availability, and therefore they click on more stuff.
Right.
It instantly fills up the pie.
Yeah. So users interact more, which generates more traffic. Because users generate more traffic, the sites are encouraged to build richer experiences. They add more capabilities, and it's a positive reinforcement cycle, right? But we're always kind of bumping up against that demand.
And it seems to me that there's another thing going on, which is that there's a world which is sort of bifurcating between, let's say, you're sitting here in Silicon Valley with a 4K monitor and a gigabit connection to the internet, and all the websites you want to visit are in San Jose, versus someone who's elsewhere in the world. Even myself in London, I typically on my phone get 3G access. So what's happening with that?
Well, actually, most of Europe is still relying on 3G. The chances of you being connected to a 4G network in Europe right now are basically a coin flip. In big cities, you have a much higher chance. In 3G, not so much. Or sorry, in other areas, not so much. But I think maybe let's actually take a step back, right? So the topic here is 2020, right? It's like, I suck at predicting the future. I think predicting the future is really hard, especially in technology, given the rate of change. So as far as I can tell, 10 years out, we're going to have flying cars, singularity, and IPv6 in that order.
But 5 years out?
So 5 years out is kind of like, it's something I can sort of reason about. It's like you take some crazy technology that's kind of on the cusp, and you're like, 5 years out, I'm sure we'll solve all the problems by then, right? So 5 years out for networks, I'm like, 5G, 5G will solve everything. We'll have plenty of bandwidth. The latency will be like 0. Everything will be awesome, right? And like you laugh, but this is the sentiment that I oftentimes get from very well-educated engineers, which is just like, there's a Moore's law, and things are getting faster. We'll get more bandwidth. So yeah, my site's kind of slow today, but if I just kind of sit on it, in a year we'll get better networks, and everything will be much better. And they're not wrong, except that they are. In 5 years, things will be a lot better, but they'll also be the same. So, and what I mean by that is, we'll deploy more networks, more denser networks, right? So we'll work on the last mile connectivity. So we'll bring more bandwidth to the edge, if you will. So you'll have more reliable experience. We will also kind of clamp down the latency a little bit more. As we already said, we're already kind of at the cusp of what we can do with physics, so it's not going to be a dramatic change. 4G is gives you 50 to 60% or 50 to 60 millisecond latency. With mobile networks, we're going to be in that range. So those things are not going to change that much. That's all good. That's going to be improvements. At the same time, as we heard in the previous talk, we're going to bring in a lot of new users online. Depending on the reports you read or projections, it's couple of billion users. They're going to be coming online in markets which are still dominated by 2G. Actually, by 2020, many people don't realize this, but 2G is still the most prevalent network type in the world. By 2020, we're projected to have some turndown of those networks within the United States. But a lot of the other markets will still heavily rely on 2G. We'll also have balloons and planes and other cool and crazy projects flying and enabling connectivity in those areas. But guess what? Those are going to be high latency networks. They're going to be like your friend in Australia or worse with 300 millisecond RTTs.
Right.
So 2020 is going to be much better. You're going to have really good performance in some areas, but you're also going to have a lot of users which are going to be subject to the same conditions that we have today. And that's kind of the performance inequality gap, right? And maybe another way to describe it is the dynamic range of performance. It's like we keep pushing the high-end performance higher and higher and higher, more bandwidth, closer servers, lower latencies, but fundamentally we're still stuck. Like we're making advancements on the low end, but due to cost reasons, due to other reasons, those things are not going to change, due to physics, unfortunately. So we need to figure out how we're going to build great, reliable experiences that span that range, where you're able to get really high throughput and you can view a really awesome video, and then 10 minutes later, you're in some other location in the tube, and the connectivity is not so great, because now you're sharing it with 150 other people or more.
And at the same time, our expectations continue to get more and more difficult, right? We expect to be able to, get that Uber to be in the app instantaneously, and the websites to be rich.
Right, and I think that's the challenge of many modern applications, because you deliver that great experience once, the user sees it, they're like, this is great, I want more of it. And once they've seen it, it cannot be unseen, right? Because it's like, well, I had that experience, and I want it now. And it's up to us to figure out the kind of the architecture, both at the network layer and at the application layer, right, and the protocols in between for how to enable that.
So let's talk about this. Let's get a little bit more technical. Let's talk about the protocol. So recently, HTTP, the protocol used for the web, has been kind of upgraded to a thing called HTTP2.
Yep.
Tell us about that. What does it do?
So HTTP2 addresses a lot of the, I want to say simple, but maybe not so simple. A lot of the technical limitations in the previous protocol, which was designed for an era where we were fetching documents. And the document consisted of mostly text and maybe an occasional side resource like an image. Today, we still deliver pages, but we deliver applications mostly. And applications are composed of many different resources. This comes back to our kind of that resource graph that you need to fetch. And the protocol is inefficient in how it fetches that. So as a browser, we have to fetch anywhere between 60 to 100 to several hundred resources to compose your average page. That requires making a lot of connections, making a lot of handshakes, doing a lot of round trips that are unnecessary. So HTTP tries to address that by just kind of coalescing more of the things into fewer number of connections with a little bit better compression, and it's an incremental improvement. Like as a user, you wouldn't even see the difference. As a technical user, you have to update your server and the client, and hopefully things work better. And it turns out that now that this technology has been rolling out for about a year, so the standard went to RFC in May of last year, I believe, right? And so it's been over a year. And depending on your application, you'll see improvements anywhere from a couple of percentage points to 30 or 50%. So on some Google properties, we've seen significant improvements in performance by just switching that protocol.
And how do you go about something like that? I mean, that's fundamentally a bit of the internet being changed, right? So
right.
How does that sort of rollout occur?
Well, I think for Speedy, so HTTP2, and then there's a Speedy for those of you that follow that whole kind of arc of development. So at Google, we started a project called Speedy back in 2007, 2008. That was kind of the early incubation, and started working on ideas for how we could improve HTTP. After about 3 years with some experimental experience, we actually put it into Chrome. We built the implementation. We built the implementation on our Google servers, on our GFEs, and we were able to gather data from out in the wild. It turns out that for a lot of the stuff, due to the complexities of the real world and the networks, it's very hard to build a model. It's easy to build a model, but most models are incorrect because they don't capture the wide variety of weird and interesting behaviors on the web. So once we had that data, we saw that there's significant improvements. So we engaged IETF and kind of through a collaboration there over the next couple of years, we arrived at HTTP2. So to answer your question, I guess it's that incremental release. And I guess the next step there is actually quick, which is, so Jana, I think, is going to talk about that later today. It's effectively HTTP over UDP. And we're following the same path there. Incremental deployments, trying to learn, and trying to accelerate that rate of learning.
Now, there's another thing I think has gone on when we've gone from the 56K world to where we are today, which is that during that modem world, it was quite common for websites to fail because your internet connection didn't work, or someone picked up the phone and tried to have a phone conversation and the modem dropped. Then we got internet connections that actually work most of the time, and we got used to connectivity being there, and then we moved to mobile.
Yep.
And now there's a strange thing going on where websites on a desktop machine might work perfectly because you've got a connection which is very, very good, and then you go on the mobile device and you're in a kind of hairy environment where the internet can disappear. So how are we going to do with that? Because I think that's another web performance.
So there's two problems there, right? One is the variability in performance, which comes back to the dynamic range. So how do I deliver an application that is reliable in terms of the experience I can provide to the user? Like when I click that icon on my launcher, I want, regardless of what my connection type, whether I'm offline or offline, I want some feedback. I don't want to sit there for a minute and then for you to show me the dinosaur page. Terrible experience, right? And also, even if you're connected, so in Chrome, we track failed navigations. And I think we're talking about this backstage. Those numbers are really, really scary to me. So when we look at the failed navigation rate, we see about 10% failed navigations for users that are on 2G networks.
So 1 in 10 times they go to a website, it simply doesn't work.
Right. They may wait for a period of time, anywhere from 10 seconds to a minute, and they'll get a page saying, they'll get the dinosaur page, which is terrible. On 3G, it gets a little bit better. It's somewhere between 3 and 5%, depending on which region you're in. But even on 4G, it's 1%, right? So 1 in 100. So that's just the reality of the network. Sometimes you're just offline, right? And first time I saw these numbers, I was shocked. And you may be thinking, like, oh man, those Chrome guys, right? They don't know what they're doing. 10% failure rate. But then actually, if you dig into the statistics for the reliability of the different networks, so OpenSignal, if you guys are familiar, does some really interesting reports into reliability of networks and kind of doing studies in different geographies. They have really interesting data that shows the way they measure it is they have an app on your phone, so you can install it as a consumer. And periodically, they just wake up and they just ping their own server to see, like, am I up? What's the RTT? And they find that on, say, in UK in particular, on 2G, for Vodafone, and I'm not picking on Vodafone, this is just the example that pops into my mind, the reliability rate for 2G is about 89%. So that's 11% of time. The device says it's connected. It's not that it's offline. It says it's connected to a network, but it is unable to make a connection. Right? So being offline is not an exception, it's the rule. Being slow is not an exception, it's the rule. And you have to design your applications to kind of work with that.
Now, I think that's an interesting point about designing applications to work for that, because it seems to me that we've got a bit of a missing piece here, which is how do the software developers who build web applications actually build stuff to cope with this situation?
Yeah, and we've had a couple of attempts at this. Some of the early incarnations were like Google Gears, back in 2006, 2007. Then we had Application Cache, which was another project. And now we're kind of doing the third take, which is service workers. So the idea there is to enable kind of new primitives in a browser that will allow you to take control over each request as it flows out of the out of the client, and implement your own logic to say, hey, I'm making a request for this image, but I'm offline. How do you want to react to that? So today, that would just fail, and you would get the dinosaur page, right? But there, now that you can intercept it, you can actually say, well, let me reach into my cache, which I also have control over, pull out maybe a meaningful error page, or pull out a previous version of the article and just give you that and notify you that, hey, you're offline, but next time you go online, I will sync new data. So you can provide a resilient experience even despite that network. And where it starts to get really interesting is not only just the offline case, but also kind of the timing case of the latency tails. So say you want to provide a reliable response within 500 milliseconds, but you just so happen to be on an overloaded network. You can actually observe that the request has gone out and just start a timer and just say, after 500 milliseconds, I'm just going to say, I'll let it proceed, but I'm going to respond to the user and say, like, it's taking a while. Here's the thing that I have right now. I'll update it later. So now you as a user have a predictable experience, which is something that's been missing. It's a critical piece.
So it seems if we try and project ourselves to 2020, we're going to have very fast networks in some places, still have the speed of light. We haven't managed to break the speed of light yet, so that's still going to be there. And perhaps the big gap is that if we do something today, perhaps we should move all the developers from Silicon Valley into the boonies somewhere where they have bad internet, and they'll come up with a programming solution for making these applications. The other thing is that there is hope for Australia, because it's actually drifting northwards at a few seconds. So it is actually getting closer.
Right, 2 inches a year, right?
2 inches a year, but still, if we wait long enough, it'll actually be...
In like 10,000 years, we'll shave off a couple of milliseconds.
Good internet. All right, well, thank you so much for chatting. I would love to open it up to questions from the audience about the web performance. Do we have a question? Yes, there's a question right in the back there.
Hi. You talked a little bit about IPv6 and HTTP2. In 2020, what protocols that we take for granted now will have to be re-engineered?
That's a great question. I'm curious to hear your thoughts here as well. So I think IPv6 will actually be a thing, like for real this time. We've been saying that for 20 years now, but I think it's true because, first of all, actually in the United States, or in North America, I should say, most of the mobile traffic is already over IPv6, more than 50% as of this year, which is really encouraging. So it turns out that mobile networks really want IPv6, and that's the primary source where that growth is coming from. So I think that's going to continue. Also, if you look at the projections or at the growth rate for IPv6, just in terms of overall adoption, so at Google we track this and we have a public dashboard, over the last 3 years it has doubled every year, which is to say it went from like 0.5% to 1%. But at this point it's actually 10%. And if you just project that out, I think in 5 years we'll be in a pretty interesting different place. And that will enable a new class of applications, which is nice. I'm really hopeful and optimistic about the efforts with Quick and UDP in particular. So TCP is great, it is the foundation of the internet, but it is also somewhat of an ossified protocol that is not able to change as rapidly as we want. And I think many people will argue that work with mobile networks that we need to adjust faster and in more interesting ways, better and more interesting congestion control algorithms and other things. And I think that's what Quick is bringing to the table. If you look at the last 2 years of our work on Quick within Google, we've been able to deploy like 20 or 30 versions, iterations of the protocol. In the meantime, there has been 0 versions of TCP released. Right? So we're able to innovate at a much faster pace because the entire network stack lives in the client. We're not dependent on the operating system, which is the ossified layer, to actually rev the whole thing. So the rate of learning will be very interesting. And I think this will enable more interesting real-time applications, video certainly, and all the rest.
So my quick answer to that would be that I think that in 5 years' time, people using unencrypted protocols will be pariahs, basically. So
Yep.
what are you doing? Why are you using HTTP now? Or why are you using something that's unencrypted? I think that's the big change. We
Yep.
see it now.
Yep.
We see about a quarter of the requests that go to our sites are encrypted. And we believe that, in 5 years' time, that will flip and it'll be unusual to not encrypt things.
Yeah, security is one theme that we have not touched on, but that's definitely a big area of focus for everybody. Yeah.
Is there another question? Yes, there's one down here.
I guess it does come into a more obvious question about, not being able to bribe God, as Dave Clark would say about, being stuck with the latency we have. If you look at applications becoming more interactive, and I'm thinking of, within this 200 millisecond, 100 millisecond twitch, just AR, so at what point do you expect that there's actually a distribution or refactoring of applications that have to take place, and we just go accept that we've got to start moving things to an edge or a more distributed edge infrastructure, which is part of the answer for Australia.
Well, I think it's already happening. It's already a thing for, like, if you look at any large organization, I can speak for Google, right? We have lots of users in Australia. It's effectively unacceptable for us to incur that round trip to like Asia or to North America for every TCP request. So we move data closer and we then replicate it. We move data into Australia or as close as we can, and that's exactly the service that any CDN will offer. So I think that's already a best practice. I imagine that it will continue to become hopefully easier for many other smaller applications to deploy, and CloudFlare is doing a lot of great work in that space. Like it used to be a very complicated thing. Now it's basically a sign-up form and a button. Hopefully in the future it'll be even easier. So yeah.
Ilya, thanks so much for joining us this morning. It's great to have you on stage.
Thank you.